In nature, many processes can be modeled by using signals. For example, let's assume that I have a time signal, which is in general a very random signal, so the signal can be very random, and I can call the signal x of t. This signal is input into a 1 degree of freedom system, or in general I can call it just a SDOF system, SDOF. I'm assuming that the system is linear, and we have some output which I can call y of t. The function that represents the system is generally called transfer function. So the system has a function which can be expressed in the time domain, or if we take the Fourier transform, we get some capital G, let's say, of omega, which is just the Fourier transform of g of t. So we perform the Fourier transform in this step here. And this function here acts as a filter for the function x of t. So it means that, for example, if we take a look at the spectral domain, the function x of t in general can be expressed in terms of the sum of sinusoids or complex exponentials, because we can approximate any function by using a Fourier series, not just a Fourier transform. And the Fourier transform is more general for signals that are not periodic, but we can also use the Fourier series to approximate our signal. It is pretty general for us to consider a signal that can be expanded in a Fourier series, which in general can be expressed using this formula: sum over n from minus infinity to plus infinity of some coefficient c sub n times e to the plus I omega sub n, where omega sub n is just equal to 2 pi times an integer n divided by the duration of the signal, which is just given by t. And then the signal is considered to be replicated in all those intervals that are periodic by period t. So we can assume that t is very, very large, for example, and if it goes to infinity, we get back the Fourier transform. But this is just technicalities that I don't want to get into to avoid misunderstandings. So I'm just going to consider signals that can be represented by using the Fourier series, and I also need to have the time variable here in the complex exponential. So sorry, I missed this time variable here. These signals in nature can be found very frequently because, for example, we might have that this signal here might represent, for example, vibrations that are acting, let's say, on mechanical components of automobiles or vehicles, whatever you like. But we could also have other signals. For example, we could have electrical signals that are filtered by our ears, our human ears. So in that case, this linear system is represented by our ear, which filters, for example, music signals, and then in the output we get some signal that occurs in our brain, and then our brain will just try to interpret the data that come from nature. This is another example, another very interesting example. And in most situations, these input signals are random in general. So I will rewrite it here: random signals, meaning that we can think the signal x of t as having a distribution, which I might call some probability density p of x, and we would like to describe this probability density. Also, in the subsequent lectures, we will talk about a very important concept. When we talk about stochastic processes, these signals are also called stochastic processes, and we will discuss the famous ergodic theorem, which is something that might seem very theoretical, but it underlies the world that we live in. Most signals can be considered to be ergodic, and we will understand what this word means without using very fancy mathematical formulae, but we will try to explain this concept more concretely, or if you want, intuitively.